Good evening and welcome to Lowell Observatory's ongoing celebration of the 125th anniversary of the construction of this telescope right behind me, the Clark 24-inch refractor. My name is Kevin Schindler and I'm the Historian and Public Information Officer here at Lowell Observatory. And I'm so excited to be here again this month to celebrate this telescope, really one of the most storied telescopes in the world, the legacy of research that was done with it, the educational programming that has been done with it, and the fact that today, during non-COVID times, visitors from around the world can come here and look through this telescope, just like Percival Lowell did, and discover the universe for themselves, just like Uncle Percy did. So we're really excited to be able to celebrate this telescope that was built 16 years before Arizona was even a state. And this coverage tonight is made possible by our friends of Lowell Observatory that supports what we do, and we're just pleased to be able to share this. So like we've been doing this year, celebrating the telescope, we're going to talk a little history of the telescope, because there's so many really interesting aspects of it, how it works, people that have looked through it, some of the science that's been done with it. Tonight, we're going to talk about the clock drive and how that has changed through the years, and I'll explain that in a minute. And then we're going to talk about what this telescope is looking at. Sarah Bircher, our manager for public programs, is operating the telescope, and you'll be able to see live views of Saturn. A little bit later, Dr. Amanda Bosh is going to be with us. And as we talk about some of the historic research that was done in Saturn, then we'll go to modern times and some of the research that Amanda has been involved with. So we will be here for about 45 minutes talking about all sorts of things. If you have any questions, post them on the YouTube channel, and our crack staff will get those questions to us, and we'll try to answer whatever comes in. So let me share my screen here and show a couple slides. And so I mentioned that we're going to talk about one aspect of the telescope, and that's the clock drive. So the clock drive, if you imagine a telescope, if you've ever got a little telescope like from Walmart or a place like that, and you set it up and look at it, before you know it, if you're looking at something in the sky, you don't see it anymore. That's because the Earth is spinning. If you imagine, kind of see my arm is, my elbow is the Earth and my arm is the telescope. As the Earth spins around, the telescope isn't going to be looking at the same thing. We have to have something on a telescope, moving the telescope in the opposite direction of the Earth spinning, so it stays focused on that object. And that's, there are different terms for it, but clock drive is one of those. And the term clock drive goes back years, because here's a picture that was taken of the telescope when it was in Mexico back in 1896. When this was first built, the telescope, Percival Lowell founded the observatory in 1894. He borrowed a couple telescopes, and then he returned them. And in 1896, he got this new telescope. It was shipped here to Arizona. They tried it out, and then they took it apart and sent it to Mexico to look at Mars, where there's going to be a really great approach of Mars, a really great opposition, as it's called, when it was going to be pretty close. And so this is the telescope when it was down there. And for those of you familiar with the Clark telescope, you can tell that this is down in Mexico, partly because the base is of brick here, and today it's cement, but also the floor is flat. There's no pit here. That's what it was like when it was in Mexico. And then also there's no inner wall. That's what it looked like when it was first built. So the telescope, you know, if you're going to do observations for a long time, you want the telescope to stay on that object. And so if Percival Lowell is looking at Saturn like he did, just like we're doing tonight, he did it 125 years ago, he has this clock drive working. And initially, it's all this stuff you see back here. You see some weights here, you see this guy turning this wheel, and some cables. And it was like kind of like a grandfather clock, where you pull the chains on a clock and it lifts the weights. Those weights slowly tick down And in this case, they're attached to cables that go to what's called a governor system, and then up through the telescope to a big worm wheel, a wheel that has little gears on it, or little crenulations, and that's what turns it. So as the weights come down, they pull on this cable that turns the telescope. So that was the original kind of clock drive. There's no electricity in here. This was built before electricity, so it was all a weight-driven thing. Here's another picture, and this is after the Clark came back to Flagstaff in 1897. And we know this is 1897 or early 1898 because you can see the pitch in the floor, so we know we're in Flagstaff. But the roof, if you look at, it still has canvas. They took the canvas out and replaced it with wood in 1898. So, as we look at these old pictures, we can really date them based on some of that kind of stuff. So if we look closely, this is kind of a cruddy picture that you can see this scan is of a picture that's kind of bent, but you can see in the back here again, all of this stuff here from this box going up to the cables, up this way, and then down to the wheel and the weights. That's part of the drive system. Today, if you come in here, you won't see these weights hanging down, but what you will see is this just spectacular instrument. It's a piece of art. It's a scientific instrument. And this is a kind of something called a governor, where these two sides spin around. And then that spinning, again, is attached to a cable, and that goes up through the telescope to turn the telescope. So this, when we renovated the telescope in 2015, our staff opened this big gray box and found this inside. It hadn't been used in decades. So we have it open today so you can see it. We don't use it because today we have modern electric stepper motors, and those are very efficient and easy to use. There's really not much care with it relatively. And so these work pretty well today, this electric system. So it, through the years, just, imagine when this was built in 1896, there's no electricity here. We wouldn't have the lights on. And so some of that's changed. But on the other hand, we still use the telescope pretty much the same way. We still have a clock drive. It's just a different type. Sarah's up there on the ladder, just like Percival might have been, a different ladder. This is the OSHA-approved ladder we use today. We have Percival's classic old wooden ladder it's a nice showpiece, but we don't use it too much anymore. So it's neat to look at a lot of these different components that are in here. So the clock drive is one of those. So tonight is really exciting. We've been looking at different things throughout the year as we celebrate the 125th anniversary of the telescope. What we're celebrating is this heritage of research and sharing the results of those discoveries with people around the world. That's the goal of the observatory, is to share the excitement and thrill of discovery. And so throughout the year, every month, we've talked about different things and we've viewed things through the telescope, and they're all objects that were studied with this telescope through the years. So we've talked about the moon, we've talked about some clusters, planets and such. Tonight is really neat because we have one of the most iconic nighttime things there is, Saturn. We're familiar with the rings. It's not the only planet with rings. There are three others in our solar system. The gas giants, Saturn, or Jupiter, Uranus, and Neptune. But Saturn's rings, which we're going to talk about a little bit later, they're just so much more extensive. And the material they're made of is, like snowy white. And so it reflects light really well. It's easy to see. And so Saturn we could talk about Saturn all night because there's so much neat stuff about it. Its density is so light. If you could build a bathtub big enough, it would float in there because it's not very dense. And so there's a lot of stuff to talk about. But what I want to do first, before we bring Amanda on, is to talk about just a little bit of the historic research that was done. Percival Lowell founded the observatory initially to look at Mars and he was hoping to prove that there was intelligent life there. But as he's studying Mars, he also studied the other planets because he was trying to come up with an understanding of how the planets develop and evolve over time. And so he studied them all. And this is a drawing that, because this is before cameras, late 1890s, early 1900s. This is a drawing that he and E.C. Slipher worked on together. We've got some moths flying around here. And so E.C. Slipher was one of the astronomers here at Lowell that worked with Percival. He spent his entire career here, as did his brother, V.M. Slipher. V.M. is known for using this telescope and becoming the first person to detect that the universe is expanding, while E.C. was a planetary photographer and at one time photographed more planets than anybody else in the world. He was a photography expert, and in fact, he developed a lot of techniques that we call image stacking today. So a real pioneer. So this is an interesting drawing of Mars because it has these lines on here. That Percival wasn't the only one to see these, but they called them torres. And there are different ideas of what they might be, like maybe rings collapsing within the planet because the planet is gas. But we know, like some of the things we see on old drawings, these things actually don't exist. Years later, not too many years, but E.C. Slipher, here he is. And here he is on a telescope with a camera. And this long thing right here is a camera. So he's looking through a secondary telescope's eyepiece. The main telescope would normally have an eyepiece right around here. They took the eyepiece off and put this camera on, and the camera comes all the way down here, and you have a little device here called a plate holder. And that holds a glass photographic plate. That's how you would take images. It's like a big piece of film. And so this is how he would take pictures with this telescope. And these are some that he took. And you can see it's a little fuzzy, but these are from 1915, 1917. And you can see the divisions in rings pretty easily. You can see a lot of the belts and zones in Saturn. And so this was a really good image 100 years ago. Of course, we've come a long way since then, but this research that E.C. Slipher did, and especially his learning how to do image stacking, was really important for future astronomy, for future astrophotography and capturing images. Today, we have telescopes like the Lowell Discovery Telescope with this imager on it that captures spectacular images of celestial objects. And we talked about that last month on the Clark 125th. So, while by today's standards, and we're going to look at some pictures in just a minute with Amanda that put these to shame in some ways, and yet for 100 years ago, these were really good images and allowed us to learn a lot about Saturn. So let's take a break for a second from the history, and now we're going to, talk about, kind of come up to the present, because, we talk about the history of this telescope, 125 years. That in itself is really remarkable. But what's so important is that the work that was done laid the foundation for what our astronomers are doing today, extending our knowledge of the solar system and beyond. And one of those astronomers that's helping us do that is Dr. Amanda Bosh, who's going to come over right now. And Amanda has been with Lowell Observatory since 1980s, affiliated with the observatory as a student. Did you have a postdoc here?
I had a postdoc.
A postdoc here, has been on staff in different capacities. So maybe you can tell about what you do here. Absolutely. You're not just an astronomer, but you do other things.
My title right now is the Observatory Operations Manager. And so what that means is that I make sure that the telescopes are working on the different, at our different sites. So Mars Hill, Anderson Mesa, and Happy Jack, the Lowell Discovery Telescope.
So that's a full-time job in itself.
It is a full-time job, yes.
But you also do astronomy.
Yes.
The thing you went to school for somewhere.
In my copious free time.
Yes. And so you see these images that E.C. Slipher captured of Saturn 100 years ago. Now let's look at some more modern ones and have you talk about those a little bit.
Let's do that. There we go. This is a spectacular image of Saturn taken by the cameras on the Hubble Space Telescope just a couple of years ago. And I put this up here just so that we could get a really high resolution image of Saturn so we can talk about some of the aspects of it. And so if you look just at the ball of Saturn, it looks vaguely Jupiter-ish, right? It has the bands going across. But then, of course, the thing about Saturn that is the most spectacular is its rings. And I will tell you, I've done a number of just sidewalk astronomy, setups where you just have a telescope and people just walk up. And this is the one that people always, they look through the telescope at Saturn and then they go around to the front of the telescope to make sure I didn't paste a picture of Saturn there, right?
It's the same thing with the Clark telescope.
Yeah.
And it's amazing with these rings because if you think about the span of them, there's something like 175,000 miles across, but only half mile thick.
Yep, that's right. It's only, it's a kilometer. I'm thinking kilometers, sorry.
Yeah, right.
It's a kilometer thick over 280,000 kilometers in diameter. So if you were to translate that to, something that we have some experience with, and I guess we always go to football stadiums. I personally don't have experience with, but in any case, if you took a piece of paper that was as large as the football field, that would be the relative thickness of Saturn's rings.
That's remarkable.
It's just not thick at all, is the answer.
And yet they're so extensive, and that's a good point because the angle of Saturn, we see it different ways. Sometimes we see it's tilted toward us really nicely, but when we see it edge on,
that's right.
You might not even see the rings at all.
Yeah, that's called a ring plane crossing. It happens roughly every 15 years. And that is when, Saturn is not, wobbling. Well, it is a little bit, but it's not wobbling, but it's mostly the orbit around the sun and then our position. And so just how everything aligns there. And so roughly once every 15 years-ish, we will be aligned with the equator plane of Saturn, which is where the rings are. And the rings will appear to disappear. They don't actually disappear, but they become invisible. And this is something that Galileo noticed back in 1612, when he was first looking at Saturn with his very small telescope. He noticed that it had these extensions on the side. He didn't know what they were, and he couldn't really tell that they were rings. That was in 1610. But then in 1612, they disappeared. And then they came back in 1613, and that's because there was a ring plane crossing in 1612.
And Galileo didn't know what to make of it.
He did not.
It wasn't until Huygens the next century or two centuries.
1685, I think. Yeah. To where Huygens, he had a better telescope. That's often how these discoveries are made. You build a bigger telescope so you can get better resolution. And Huygens was able to tell that it was not ears on the side of Saturn or two large satellites. It was actually a ring that encircled the planet and touched it nowhere. And that's very important because people at first were thinking, it was a solid ring that maybe was somehow attached to Saturn, but just because of the laws of motion, that won't work.
Yeah.
And get sheared apart. Yeah.
And this is we're sitting here looking at this image, which is a Hubble telescope image. And then we have the historic Clark behind us. And we looked at those images that they captured back then. And that was pretty good for back then.
It was really good.
But the technology 100 years later, this telescope, telescopes, the bigger they are, the more light you can gather. This one has a diameter of 24 inches or so 2 feet. Yeah. And the Lowell Discovery telescope is 14 feet. Mm-hmm. That's a considerably more amount,
more. Yep.
And so that makes a really big difference. And in the case of Hubble, it's not as big as the LDT, smaller, but it's up there above the atmosphere.
That's right. And so if you just look at the rings here, and you can see this in the pictures from the Clark, you can see that there are different ring regions, right? There's the brighter region and then a darker region outside of it and then another bright region. So that brightest region is called the B ring. Outside of that dark lane, it's called the A ring.
We can use this.
Oh, excellent. Yep. So this is the A ring out here. This is the B ring. And this is the C ring. These are the things that we see. This is the Cassini division. And when we get to take a look through the Clark, we should be able to see these as well. You won't be able to see the C ring. I've lost the pointer. Oh, there it went. Okay, thank you. You won't be able to see the C ring, but you will be able to see the A and the B rings with maybe a little bit of a gap between them. And then there are more rings outside here. There's the F ring and the G ring and the E ring, and there's an even fainter ring inside here called the D ring.
Okay, and that's a good point. Maybe we can check with Sarah when we can take a look, or maybe our team, we can take a look at Saturn and get it up on the screen. I don't think we're able to see it here, but
okay.
They'll get it up there so our viewers can see it.
Excellent.
So yeah, so let's talk a little bit more about Saturn.
Yeah.
Okay, before we do that, we have noise coming. First, there's a train, and we have, I think it's 110 trains a day that go through Flagstaff now. And we also have to move the dome. Otherwise, if we don't move the dome, the telescope, as it's tracking and tracking and tracking, because that clock drive, it'll eventually look at the ceiling, and that's not a very good view. So Sarah moved it, and it looks like we're transitioning to the Clark view now. So let's talk a little bit more about this. I'll let you move that as we need.
Yeah. So when you're looking at Saturn's rings here, one of the things that you might start thinking about is, why does it even have rings? And it's a really good question, because if you look at material in orbit around a planet, there's a number of forces that are acting on it. So that ring material should not stay there for very long at all, just almost no time at all, only like 1 million years, really short period of time. But it has rings. And so one of the things, we don't like to think that we're living in a very special time. So there must be something that keeps the rings there. And so this is some research that I did when I was a graduate student. It was the subject of my thesis, is really to look at where exactly the rings are so we can identify mechanisms for keeping them there. And so the main thing that constrains the rings against just spreading outward entirely so we don't see them anymore is something called a resonance, and with an external satellite. And this is just, if you're, so for instance, if a ring particle is going around twice, then an external moon would be going around once in that same time. And so that, because they match up, and every 2 orbits around, they would be in the same configuration, they would get a little gravitational kick. That's a resonance. So if you don't have those integer ratios, then the little kick you get from gravity is just not as strong.
So where else do you see resonances?
Well, we see them a lot. I mean, you can describe most of what's going on here in Saturn's rings, and some things that you don't see as well by resonances. You can think about it also when you're on the playground and you're pushing somebody on a swing. Right. So if you push that person just sort of at the right frequency, they're going to go higher and higher. Right. But if you're just sort of randomly coming in and pushing them at a random spot in their swing, then first of all, they're just going to bowl you over, and they're not going to end up going higher and higher. So we can think about it. Can you think of any other examples?
That's a great one.
Okay.
Yep. And I was reminded of a humorist. I can't remember his name offhand, but he said that the rings of Saturn consisted of lost airline luggage. And we're pretty sure it's not that.
Yeah, no. But what you notice is that it's really bright, right? So when we think about it, well, what could it be made out of? Well, it has to be something that's really bright. What is really bright? Well, ice, exactly. In the solar system, when we see something that is really bright, it is ice, water ice generally, and not only that, but it's fresh. Because if you take water ice and you put it out in the solar system, then it'll get bombarded by high energy particles and it will darken over time. So bright ice is fresh ice. And so that means they're bumping up against each other. And if there's any sort of crust that forms, it breaks apart and dissipates. And so if you look at, you can prove this by looking at Saturn with a spectrograph and then just breaking apart those different wavelengths of light, and each compound has a very specific fingerprint via wavelength, and so you can show that it is water ice. And so where did these come from? Well, if you look at the satellites in the Saturn system, they often have a lot of water ice in them, and so one of the theories is that it might have been a satellite that was then broken apart. And what we're seeing is the remainders of that satellite. So
how many satellites does Saturn have right now?
Right now it has
today?
And not to imply that it's creating them or anything like that, but just satellites that we know about. It has 72. Did I get that right?
I think 82.
82. Yes, it has 82 moons or satellites that we know about. And the largest one is Titan, which is about 50% larger than our moon. And the smallest one is I don't know how to pronounce this, Aegeon, which is less than a kilometer.
So maybe you can talk about Titan just briefly, because that's a moon that's in the news fairly often.
Yeah.
And there's, missions going there. And why is that? Why is it so interesting?
Yeah, so Titan is a really interesting satellite because it is, like I said, it's smaller than our moon. Our moon is smaller than it. It's larger than our moon, but it has a really substantial atmosphere. In fact, at the surface, its atmosphere is roughly the same pressure as the Earth's atmosphere, but it's made out of different things. And so it has different gases in the atmosphere, but it also has lakes and rivers on its surface that we can see. We actually couldn't see that for a while because its atmosphere was so thick, we couldn't see through it. And so not until you found the right wavelength bands where the atmosphere was transparent, not until we found those that you could see through to see what was on the surface. And now you can see that there are lakes and rivers, and you can see things changing in the lakes, in the shoreline. So what that means is that there is probably a precipitation cycle, not water, but something is raining down and filling up the lakes and then evaporating again. And so, and you can see lots of geologic features that are due to rivers on the surface of Titan. So there is coming up a spacecraft, the Dragonfly mission to Titan. And what it's going to do is, it's really cool. It's going to fly little hovercrafts, quadcopters on the surface of Titan. And these little things, they look like little dragonflies, and they'll just sort of hop around, fly to various places, test the materials there, and just look at what the composition is, what the composition differences are, and search for conditions that would be conducive to life.
And that's something that Corey Cody just asked. How would you detect it?
Right. And so we're not looking for some alien to drive up in a rover or something like that. Yeah, no. And so that would be cool, but probably not. And so what we would be looking for is these chemicals that would be conducive. And so that would support life. And I don't have a list with me right now, but there is a list that the mission is looking for. Yeah. And
we've got another question we should answer now. We had the view, the live view through the Clark, and Mike Kelly asked about the pulsating nature of view and why that is. So maybe talk about that for a second.
So we are as we're viewing from here, we're viewing through our atmosphere. It's kind of like viewing through a fishbowl, where you're looking through the water that's going up, and you have to look through all of that. And so our atmosphere is in a constant state of flux. It's moving. There are wind currents, temperature differences, and so all of that. A small temperature difference will change the refractivity of the atmosphere, and so that'll make the Saturn's image shift. And so that's what we're seeing here, is just small differences in our atmosphere that make the Saturn image move around a little bit, and then also kind of look sharper and then not as sharp.
So it's important to restate that it's our atmosphere. It's not the planet out there. It's our atmosphere.
Yep.
And we got another question from King Lear. Wow. How fresh is the ice in Saturn's ring? So, how often is it regenerated? How old is it? Right.
And so, when I said that fresh, bright ice is fresh ice, that's still on a, for us, it's on a long time scale, maybe a couple, thousands to millions of years. But when we look at something out in the solar system, we just make the assumption that it's been there for a very long time and that we're not viewing it at a very special time. When you ask, how old are Saturn's rings, it really does depend on why Saturn has rings. So I had that, I put forth that one theory that it was a satellite that was disrupted and broken into it, lots of pieces. That's just one theory. And if that were the case, then that probably happened at the beginning of the solar system, so 4.5 billion years ago. But there are other theories. So one of them is that Saturn captured a comet that came nearby, or several comets that came too close, and then shredded them apart. And then here we have them, then they stayed as rings. And so if that were the cause of Saturn's rings, then that could have happened more recently. So we really don't know how old Saturn's rings are.
So are there any other bodies that we found with rings that are close to Saturn's? And maybe then, compare them to the rings of the other planets. Right.
So Saturn's ring system is the most massive that we have in our solar system. It's the brightest, it's the easiest to observe, it's the most dramatic ring system. And for a long time, Saturn was a planet that was known to the ancients. Right. And so the ring system was there, presumably at that time, but we couldn't see it until we had the telescope. And so from the 1600s, we've been viewing Saturn's rings, and they haven't changed in appearance. So from our perspective, at that time, Saturn was the only planet that had rings, and this is what rings looked like. It wasn't until more recently, 1977, in fact, when the second ring system in our solar system was discovered. It had been there already, we just couldn't see it. And this was in 1977, James Elliott, who was an astronomer here as well, along with Bob Millis and several other astronomers at Lowell Observatory, were observing an occultation by the planet Uranus. Now, an occultation is when a planet passes in front of a background star, and we measure the brightness from that planet, and from the star, rather, as the planet passes in front of it. And then Professor Elliott was trying to look at the atmosphere of Uranus because, nobody knew it had rings. But he was my thesis advisor, and I can tell you he was always very, very careful. And so even though he knew when the atmosphere occultation was going to start, he started observing an hour or two early because that's just the way he was. And so, but that turned out to be really fortuitous because what he saw before the planet occultation was that there were some dips in the light curve, very short, very small dips, and then the planet occultation, and then on the other side, there were symmetric dips on the other side. And so that turned out to be the rings around Uranus. And we have a picture of it that we can go to at some point.
Okay, while you talk, I'll scan through, but maybe you can talk about that the occultation a little bit more, because it wasn't, we think about looking at stuff in space with telescopes, but they use special telescopes also that weren't on the ground.
Right. So this particular event was, well, there were some telescopes on the ground, but also what they used was a telescope on board the Kuiper Airborne Observatory. So it was a C-131 aircraft with a let's see, I think it was a 0.8 meter telescope in it, just in a hole cut in the side. And this was necessary, because the occultation path was going to go over a lot of water. And so there's not a lot of places to put telescopes, but an airborne observatory will take you there. The Kuiper Airborne Observatory has been retired. I think it was retired in 1995, 1994, something like that, and has been, the next generation airborne observatory is SOFIA, the Stratospheric Observatory for Infrared Astronomy. And so, but the thing about occultations is that we can use ground-based telescopes, we can use flying telescopes, we can use space telescopes, but what it gets us is a very close-up, a very high-resolution, spatial resolution view of whatever it is that we're looking at from very far away, because we're not trying to image it. If we were trying to take an image of it, we would be subject to whatever the atmosphere is doing to us, but that's not what we're doing. Now, this image here is an image taken by the Keck telescope of Uranus, and you can see the rings there. They kind of look like they're drawn in, but they're not. But the reason we could see the rings in these images, and this was taken much more recently, is that these rings, this was taken in infrared wavelengths, where the planet is very dark because it was taken in a methane absorption band, and Uranus has a lot of methane in its atmosphere, but the rings do not. And so at this wavelength, Uranus is relatively dark, and so we can see the rings here.
So what's this material versus compared to that of Saturn's?
So that's a really good question, and I don't know the answer to it, because the rings of Uranus are very dark. They're among the darkest material in the solar system. And if you, so that makes them difficult to study because they don't reflect a lot of light. And if you do spectroscopy on the rings, you need a big telescope like the Keck. There are no absorption features. So that means it's very difficult to identify what they're made out of. But they're dark, they're smaller particles, and so they might be, similarly to Saturn's rings, they might be made of whatever Uranian satellites are made out of. So some pieces of, but we can say that they're not ice because you would see the ice signature.
And so the same goes for the other gas giants also?
Right, right. Right. So one of the things about the discovery of the Uranian rings that I always find really interesting is there was an IAU circular that the group put out, and they told people to look for a belt of satellites around Uranus. And I asked Professor Elliott afterwards, I'm like, well, why did you say it was a belt of satellites? Because clearly it was a ring. And he said, well, at the time, everybody knew that only Saturn had rings, right? So this was a real paradigm shift to discover rings around another planet, because everybody knew that no other planets had rings, but yet Uranus did. So, and then we now know that Uranus has rings, and Neptune has rings, which were also discovered from the occultation technique. I think we have a picture here if we want to. I'm not sure if we're looking at them. Yeah, yeah. This one, there are images of Neptune's rings from Keck, but I kind of like this one here. And also it shows the ring arcs. This was taken from the Voyager 2 spacecraft. The rings were discovered in the 1980s. You can rest assured that after the Uranian rings were discovered by this stellar occultation technique, everybody ran out to their telescopes and tried to do the same technique with Neptune. It was a little harder because it didn't pass in front of stars quite as often as Uranus was at the time. And it was also difficult because people would sometimes see a dip on one side, but no dip on the other. And then the next time they looked, it wouldn't be there. So there was something really crazy about the Uranian rings. And you can see an evidence of that in this picture. See that this part over here is brighter, whereas over here is fainter. So these are called ring arcs. This is in the Adams ring. There are 5 ring arcs in this ring. And that's where there's more material clustered together, so it actually blocks the light from the star. Whereas over here, there's less material, and so it blocks the light, but just a little bit, and you can't see it quite as well. So this was another paradigm shift because rings have always been continuous around the planet, and these ring arcs are embedded within a ring, so they are continuous. But we still don't quite know what causes these ring arcs to be there. They are stable. They don't, you know, they move with the ring material, but they don't change over time. So there's if anybody wants to start a research project, that's a good one.
Well, let's go back to the moons for a second. The different planets have different number of moons, from 0 to dozens.
Yep.
Which planets have the most? And is it? I'm leading you here.
Yes, you are. So the giant planets have the most moons. So right now, Saturn has the most known moons. Again, I'm just going to make it clear that Saturn has however many moons it has, but we know of 82. Jupiter has 79 known moons. I'm looking at my list here. Uranus has 27, Neptune has 14. And then from there, you know, when we look at terrestrial type planets or Pluto, then we're talking about many fewer moons around these particular planets. Yeah. And so, you know, ring systems could be a remnant of the formation of that planet, and satellite systems. And because if you're you know, you can form a moon from this protoplanetary nebula, just from all of the material coalescing. But then if there's some disruption and that moon maybe changes its position a little bit and moves within something called the Roche zone, which is 2.5 times the planetary radius, then the differential of gravity across that body will actually break it apart. And so that could form a ring system as well. Okay.
You know, we're talking about these rings, and, you know, we've known about Saturn's rings for a long time, but, you know, we're sitting in Percival Lowell's dome.
I know.
His telescope is looking there, and you just wonder what he would be thinking if he could see some of these pictures. We're sitting at his telescope, and images aren't from the telescope, but just what he would think about all this. It's changed a lot.
It has changed a lot. I'm sure he would be fascinated. Yeah, and he would be interested in some of these questions as well. Yep.
But space has changed a lot in your time. I mean, you know, Percival Lowell passed away more than 100 years ago. But even in your time, in your career, a lot has changed in astronomy. The technology improves and we keep finding more stuff. Is there anything with Saturn and its rings that, you know, you look forward to finding out, or, you know, any big mystery that you'd like to see solved?
Well, yeah, there
Many.
many. Where do I start, right? But you know, we had an orbiter around Saturn for 13 years until 2017. That was the Cassini spacecraft, and boy, that one just got so many wonderful images. Really resolved a lot of mysteries and created some new ones as well. Can we just go back a little bit?
Sure.
Can I just do this? This one here, so the Saturn's rings again, right? And then this is a close-up of Saturn's rings taken with the Cassini spacecraft. And I've got a little blue circle there in the center. And what we see there is a satellite. It's called Pan. It's in a gap called the Encke gap. It's a smaller gap than the Cassini division. It's in the A ring. And what Pan is doing here is actually clearing that gap. By having that satellite embedded in the rings, it clears the material around it. It either just gravitationally forces the material to go back to one side or the other, or some of that material actually gathers onto the satellite itself. And you can see it here in this photo. This is again from Cassini. This is from this picture, Pan got the nickname of the ravioli moon.
Yeah.
You can see that, I think, right? So that skirt around Pan, it's in the equator there, is dust, you know, like micron-sized material that collected onto the satellite. And really is just forming that little bit of a skirt there. And that tells you right there, that tells you how thick the rings are, because the width of that skirt is the width of the rings. The satellite itself is 30 kilometers in diameter. And so you can just see, you can almost see this evolution happening within the rings. And what this does, really, what we're showing here is really how you form a moon, right? Well, how you can form a moon, or how you can form a planet from that protoplanetary disk by just sort of collecting all of that material and patting it all together and making a nice new body. And we'll go to something later that might be relevant to this.
Well, it's neat. It's neat. In Percival Lowell's time, you know, they didn't have spacecraft, telescopes, and the things that we've been able to reveal using spacecraft.
Absolutely.
We've got just a minute or two left.
Okay.
So if there are any other questions, send those in. Here's one. What would happen if the moons collided?
Yeah, so first of all, the moons that are left are not on collision paths, but what you can get is a collision from outside. You can get like a comet coming in and hitting something, hitting a moon, hitting Saturn itself. And so you would create a lot of dust. And that dust would, depending upon the trajectory, would probably be more spherically aligned in the beginning, but then after, again, a short period of time, just 1 million years or so, it would just collapse all into the equator plane, and then either dissipate if it's outside of these rings, or just become part of the rings.
Okay.
Yeah.
Well, Dr. Bosh, thanks so much for joining us tonight. I think we're out of time. It goes so fast.
It really does.
But before we go, we just want to thank everybody for joining us. We want to thank our team, Sarah, who's been operating the telescope tonight, our behind the scenes crew of Heather, Maddie, and Cody. And also we want to just mention about these live streams we're doing. This one of the 125th anniversary, some of the real popular ones like interactive stargazing, they're all made possible by our members and support from our members. So if any of you out there watching would like to know more about membership, you can get information that's posted in the chat on this, and you can also go to our website. So a lot of different ways to support the observatory. And, you know, supporting an observatory is, there's of course financial support, but just watching these programs and learning about the cosmos, that's what we're here for. That's what you're exploring the universe and sharing this excitement with people, and it's carrying on in Percival Lowell's Dome. We're carrying on the tradition. So it's a real honor for us. So thanks everybody for joining us, and we'll see you next time.